Welcome to The Deep Dive. We're the show designed to get you, our technical listeners, right to the heart of the latest AI research. Today, we're digging into LLM alignment with a really interesting paper, GT-Align, Game Theoretic Alignment of LLM Assistants for Mutual Welfare. Our mission, as always, is pretty focused. We want to pull out the core engineering insights, specifically how game theory is being used here, not just as an idea, but as like a mandatory mechanism to make LLMs genuinely cooperative. If you're involved in building the next wave of assistants, pay attention. These concepts feel foundational. Begin 1-minute short-form summary.
Okay, so the basic problem GT-Align hits head-on is this. Current LLM alignment. It often creates a kind of social dilemma, the model tries to max out its immediate reward, maybe by giving a simple answer, avoiding deep thought, and bam, you get an outcome that's actually subpar for the user. It's pretty much the classic prisoner's dilemma, really, but playing out in AI conversations.
Right, that failure to cooperate for the best outcome.
Exactly, and GT-Align's fix is, well, it's fundamental. They actually weave explicit game theoretic reasoning right into the LLM's thinking process, the chain of thought, or COT, and into its RL training.
So it's forced to think strategically. And part of that is constructing this payoff matrix for itself and the user.
Precisely. It builds a matrix, analyzes it, and then aims for what they call a mutual welfare reward, which isn't just a simple sum.
And does it work?
The results look strong. They reported about a 21.5% boost in reasoning efficiency, so better answers per token, essentially. And crucially, a 7.2% average increase in that mutual welfare score across different tasks. Plus, it seems to generalize, well, even to datasets it wasn't trained on. And 1-minute short-form summary.
Okay, let's unpack that core idea. User-LLM interaction as a sequential strategic game. Why the need to formalize it like that? What's wrong with just, turn-by-turn interaction?
Well, the problem is that standard LLMs, often trained to just maximize their immediate reward, they miss the long-term benefits of genuine cooperation. They tend to take the easy way out. So the authors formalize this. They define specific strategy spaces.
Okay.
For the user, it's basically ask a vague question, VQ, or a detailed question, DQ.
Simple enough. And for the LLM?
3 main moves. Give a direct answer, DA. Ask a clarifying question, CQ. Or provide an answer plus another question, AQ.
Got it. So let's walk through the failure case, what they call the default interaction. User asks a vague question. What happens next, typically?
The unaligned LLM, thinking individually rationally, just gives a direct answer. DA to VQ. It's low effort, low risk for the model itself.
But probably not great for the user.
Exactly. In their payoff model, this ends up as a 1-1 score. 1 for the user, 1 for the LLM. And that's the Nash equilibrium here. Neither side can improve just by changing their own move. But, crucially, it's socially suboptimal. Both are stuck in mediocrity.
The prisoner's dilemma trap again. Okay, so GT-Align aims to break out of that 1-1 state. How does the ideal interaction play out to reach the best outcome, the 3-3?
Right. This requires a multi-turn cooperative dance, and it forces the LLM to act against its immediate impulse.
Okay, this is key. You mentioned the LLM has to make a sort of sacrifice. How does that work in turn 1? Vague question comes in. The default 1-1 payoff is from giving a direct answer. How does GT-Align make it ask a clarifying question instead?
That's the core intervention. The GT-Align framework guides the LLM to choose CQ. Now, asking a question is effort, and it doesn't immediately satisfy the user's need. So in their model, the payoff in that first turn actually drops from the potential 1-1 down to 1-0. The user's utility stays at 1 initially, but the LLM gets 0 immediate payoff for its effort.
So the LLM takes a hit up front, 0 utility for itself, hoping for a better future outcome. It's like an investment.
Exactly. It's signaling cooperation and guiding the interaction. Then, in turn 2, ideally, the user sees this, provides the needed detailed question, DQ. The user's payoff then jumps, say, from 1 to 2, because they're getting closer to a good answer.
Okay, user responds cooperatively. Then turn 3.
Turn 3, the LLM follows through. It provides the high-quality answer, plus maybe another helpful question, AQ. This high-effort, high-value move finally gets both parties to the maximum welfare state. 3. The principle is clear. You only reach the best outcome if the LLM proactively guides, even at an initial cost, banking on that cooperation sequence.
All right, that makes sense strategically. So how do they actually embed this kind of economic thinking into the LLM's generation? This is where that 4-part game theoretic reasoning chain comes in, right?
Yes, precisely. It's structured to force this strategic thinking internally before the LLM responds. It's like an internal monologue made explicit.
Okay, what are the parts?
First is the thinking block. Here, the model literally writes out its qualitative reasoning, thinking about the risks, the costs, ambiguity, how to get a better answer.
So it justifies its potential moves.
Kinjet? Then comes the payoff block. This is structured data, a JSON object. The LLM has to construct this matrix itself, estimating the utility scores for both itself and the user for all the possible action pairs, like VQDA, DQ, AQ, and so on. Scores are roughly in the range of -5 to +5.
Wow. Okay, so it's not just qualitative reasoning, it's quantifying the potential outcomes.
Yeah.
And then the decision step.
That's the analysis block. Crucially, the model doesn't just show the matrix, it solves it. It analyzes the payoffs to find the actions that maximize mutual welfare according to the objective function they define.
It does its own game theory calculation.
Exactly. It's performing the strategic reasoning internally.
And only after all that, thinking, quantifying, analyzing, then we get the final response that the user actually sees.
That's right.
What's powerful here isn't just, maybe getting a better answer. It's the transparency, isn't it? You can actually read the model's economic rationale.
Absolutely. That's a huge benefit. It makes the decision-making auditable, consistent, and something you can explicitly train using reinforcement learning.
Okay, let's talk about that training objective then. The mutual welfare reward. It combines user welfare and LLM welfare. How is user welfare defined? They split it 50-50.
Yeah, for $1, it's over$5 times Q plus 0.5 times const user. $2 is answer quality, think, accuracy, safety, helpfulness, and cost users key for practical use. It penalizes things like long, verbose answers and high reasoning latency, basically wasted user time. The 50-50 split suggests, a slow, perfect answer can be just as bad as a fast, mediocre one for the user experience.
Right. Efficiency matters hugely to users. Now, the LLM's own welfare, the weighting shifts there, doesn't it?
Right.
Quality drops to 0.4 weight.
It does. For $, 0.4Q plus 0.2 cost dollars plus 0.4G. So quality still important, but slightly less so.
And cost for the LLM is weighted less too, at 0.2.
Right. Cust-LM mostly penalizes generating lots of tokens, which costs the provider money.
But there's a new term, DLAO, the game theoretic reasoning score, also weighted heavily at 0.4. What's that rewarding?
That DDL score rewards the LLM for doing the process correctly. Did it generate the reasoning chain in the right format? Did it correctly derive the payoff matrix and perform the analysis? It's basically incentivizing the model to follow the strategic methodology and manage its own costs.
So DDLO pushes the LLM to be strategic and cost-conscious, while $1 pushes it towards accuracy and speed for the user. Interesting balance. Now, aggregating these DLNLRs into the final niche, they didn't just add them up. They used the Cobb-Douglas function, scored times LALO. Why that specific mathematical form? Seems like a deliberate choice.
Oh, very deliberate. Using Cobb-Douglas, a multiplicative form, has really important properties for alignment. The big one is what they call zero dominance. Because it's a product, TRU times, if either Sever or Lawler goes to 0, meaning the model completely ignores the user, or completely ignores its own process and costs, then the whole mutual score collapses to 0. This mathematically prevents the model from finding solutions that maximize one party's welfare by totally sacrificing the other. It forces a balance.
Ah, okay, so you can't just optimize one side into oblivion.
Exactly. The other key benefit is diminishing returns. If, say, user welfare is already really high, making it even higher gives less of a boost to the overall score compared to improving LLM welfare if NOAA is currently low. It naturally pushes the optimization towards improving the weaker score, promoting fairness, and Pareto efficiency. This function helps explain why they saw that 7.2% average welfare improvement and better results on things like regret minimization.
That's a really elegant mathematical choice for ensuring balance. Okay, shifting gears slightly, let's talk practical deployment. One really neat feature they highlight is dynamic steering, changing the LLM's behavior at inference time without retraining. That sounds incredibly useful, especially if, say, pricing changes.
It's a huge practical advantage. Think about two common scenarios. First, maybe a subscription mode. The provider running the LLM wants to minimize token usage to save costs.
Right.
Second, maybe an API pricing mode. Now the user is paying per token, so they're very sensitive to length and might prefer a quicker, maybe slightly less perfect, direct answer to avoid costs.
Okay, different economic incentives. How does G2Line let you switch between these behaviors on the fly?
They use the transparency of that reasoning chain. When the policy needs to change, say, switching to API pricing, the system can actually pause the LLM's generation right after it outputs the payoff block.
It intercepts the JSON matrix.
Exactly. An external process reads that matrix, programmatically applies a penalty to the user utility values based on token cost, and then feeds the modified matrix back to the LLM to continue with its analysis step.
Wow, so the LLM receives its own calculated payoffs, but adjusted for the new pricing reality.
Precisely. And because the LLM solves the matrix it's given, its subsequent analysis and response will naturally reflect those adjusted incentives.
So in subscription mode, it might have chosen a clarifying question,
Yeah.
CQ for long-term welfare, but now, seeing the user penalized for tokens in the modified matrix under API pricing, it might shift to a direct answer, DA, because that's now calculated as better for mutual welfare under the current policy.
That's the idea. It allows for this very transparent, policy-driven control over the LLM's strategic choices
Right.
without needing to retrain the whole model. It's adjusting the objective function directly.
That is very cool. Okay, let's quickly hit the performance numbers again, focusing on what matters to engineers deploying these systems: efficiency.
Well, first off, they noted a near-perfect format score, which basically means the model reliably produced that four-part reasoning chain. That consistency is important for the whole approach to work.
Good point. Reliability first. What about cost effectiveness?
The key metric there was answer score per token, ANS token. On the math dataset, which involves complex reasoning, GTLAN showed a really impressive 31% improvement in efficiency over the best baseline.
31%, that's substantial. It means the strategic thinking isn't just better, it's more focused, less wasteful.
Seems so. It suggests the game theoretic approach leads to more cost-effective reasoning paths.
And how did it handle specific challenges? Things like safety or dealing with ambiguous questions.
Performed very well there, too. On WildGuard, for safety, it hit 97.33% total accuracy, good at identifying risks and offering safe alternatives while still being helpful. And on AmbiguQA, which tests how it handles ambiguity, it got 93% accuracy. That suggests its strategic choice to ask clarifying questions when faced with vagueness really pays off.
Strong behavioral results. And generalization. Crucial if you want to deploy this widely. Did the strategy transfer?
Apparently, yes. They tested it on several out-of-domain datasets, things like Minerva Math, AdBench for adversarial robustness, and found it still improved mutual welfare by about 10.5% and answer quality by 7.4% compared to baselines, even without specific training on those domains.
So the underlying strategic framework seems robust.
It looks that way.
And just to close the loop, they did a user study. Did humans actually prefer the GTLAN output?
They did, and the study confirmed the link. Higher calculated mutual welfare scores strongly correlated with better human satisfaction ratings, about an 11.3% improvement in how users rated the interactions.
Okay, so the math translates to real user preference.
Yeah, it seems GTLAN Giant offers this powerful, principled way to make LLM decision-making more rational, more auditable, and ultimately more aligned with what users actually want. It's moving the LLM beyond just pattern matching towards being a strategic partner.
So thinking about what this means for you, the listener, maybe building or deploying these systems, we've seen GTLAN gives providers this transparent lever, right? The ability to steer the model by tweaking that payoff matrix at inference time based on economics. That transparency is powerful, great for adaptability. But it also raises a potential issue, doesn't it? Here's the provocative thought to leave you with. If the service provider can dynamically redefine the payoffs, what stops them from tweaking it to heavily favor their welfare, maybe prioritizing cost savings above all over the user's actual needs? Yes, the Cobb-Douglas function pushes towards balance, but the definition of $2 and the specific weights or penalties applied are still up for grabs. How do we ensure in a real-world service that the definition of mutual welfare being optimized truly reflects maximum human benefit and isn't subtly shifted by the provider to prioritize their own bottom line, especially when that shift can happen with just a few lines of code modifying that payoff matrix? Something to think about.